Martine. How's it going? Can you hear me? How's it going? 10 o'clock right now. I'll probably give like a minute or two for people to join in. We've got 8 folks right now. Hopefully you can all hear and see. It appears to be working on my end. And hopefully you can all see the chat space. So if you have questions, you just type the question in the chat. If you wouldn't mind, could you please put some comments in just to make sure I know you can use the chat? Say hi. Let me know you're here. Martine is here. That's all I got so far. Also, that'll help me get a sense of the lag. Usually there's like at least a couple seconds between when I say something and you respond. Shaheen is here. Matt's here. Okay, well, that's 2 minutes in. I don't want to make people who are watching this after the recording have to wait for too long. So I'll go ahead and start. I'm going to work through the practice test. If you have any questions or comments or not sure how I did something, just participate in the chat, and I'll see your comments or thoughts, and hopefully I'll be able to respond. Also, I may run out of time. I'm going to have an hour and a half, depending on how fast we go. Practice test, I may not. If we start coming to the end and I haven't gotten to a question you had, be sure and ask it. So if there's something at the end that you want to make sure I cover, let me know and I'll be sure and cover it. But here's number 1. A says solve triangle BCD. So that means I need to find all of the side lengths and all the measures of all the angles. So I'm going to start by finding side BD. I'm going to say, let's see, a squared plus b squared equals c squared. $25 and 36, 50, 61. Cool. Then I'm going to find the 6 trigonometric ratios of angle B. Oh, sorry, I'm not done with A. I need to solve for the angles. So I found side C. Now I'm going to find angle B. I know the opposite is 5 and the adjacent is 6. So I'm going to say the tangent of angle B is equal to the opposite side 5 over the adjacent side 6, which means that angle B is equal to the inverse tangent of 5/6. And it's not one I know off the top of my head. So let's find inverse tangent of 5/6. And make sure I'm in degree mode, 39.81 degrees. Cool. And then obviously angle, let's see, that's angle D over there is the complement because the total of the angles has to be 180 degrees. So I'm going to say what is 90 minus that? 50.19 degrees. Cool. Now I'm on part B. This was part A. Solve the triangle. And on part B, I need to, whoopsie. I need to use simplest radical form to find the 6 trigonometric ratios of angle B. So I'm going to need to find the sine of angle B, the cosine of angle B, the tangent of angle B, cosecant of angle B, the secant of angle B, and the cotangent. So sine is opposite over the hypotenuse. So 5 over root 61 equals 5 root 61 over 61. Cosine of angle B is the adjacent over the hypotenuse. So 6 over root 61 equals 6 root 61 over 61. Tangent of angle B is the opposite over the adjacent, 5/6. The cosecant is the hypotenuse over the opposite, root 61 over 5. The secant is the hypotenuse over the adjacent, root 61 over 6. And the cotangent is the adjacent over the opposite. Cool. Done. Questions on number 1? Okay, seeing no questions, I'm going to move on to number 2. You guys will let me know if the sound is weird or you can't hear or anything like that, hopefully. Number 2, we had to take the same triangle and dilate it about center A by a factor of 2/3. And then we're going to explain why the trig ratios did not change. So to dilate, I'm going to say each point is going to shrink towards point A by a factor of 2/3. So currently I can see that to get from A to B, I would go up 6 and over 3. I'm going to take 2/3 of that, which is up 4 over 2. So here's my new point, B prime. Notice that this is 2/3 of the entire distance. For point C, currently to point C, I would go 1, 2, 3, 4, 5, 6, 7, 8, 9, and up 6. I'm going to go 2/3 of that, which is over 6, up 4. C prime. Cool. And then I'm going to do the same thing. Currently, it's over 9 up 11 to get to point D. So I'm going to go over 6, and let's see, 2/3 of 11, 22 thirds, which is like 7 1/3. So up 4, 5, 6, 7 1/3. Looks good. Oh, and this is D prime. So here's the triangle, B prime, C prime, D prime. I'm noting that if I drew in these lines, showing how I got from each one to the next, that again, the distance from A to B got 2/3 as long. The distance from A to D got 2/3 as long. The distance from A to C, 2/3 as long. Then I'm going to explain why triangle B prime, C prime, D prime, this triangle has the same trigonometric ratios as triangle BCD. So dilation of a figure about a point leaves angles unchanged and side lengths in, and let's see, and side lengths in the same ratio. Since trig ratios are the ratios between the sides of a right triangle, they will remain unchanged by a dilation about a point. Cool. Questions on number 2. Obviously, you wouldn't have had to have written exactly that, but something along those lines. Sweet. I don't know how interactive this review session is, but hopefully you're getting something out of it. Number 3, explain why the secant of 35 is equal to the cosecant of 55. Draw and clearly label a triangle and refer to it in your explanation. So I'm going to use a right triangle. I'm going to say that here's the 90 degrees, here's 55 degrees, here's 35 degrees. I'm going to say this triangle has sides A, B, and C. And then I'm going to say that the secant of 35 is the hypotenuse over the adjacent. So the hypotenuse is C, and the adjacent to the 35 is B. And then the cosecant of 55 equals the hypotenuse over the opposite. And the opposite of 55, well, let's see, hypotenuse is still C. The opposite of the 55, oh, that's B. Bam. So, therefore, secant of 35 equals cosecant 55. And I'm going to say something like 35 and 55 are complementary angles. The two acute angles of the same right triangle. Okay, I'm seeing a question from Tomas. I'm not done with this, but I see a question from Tomas that says, will the problems on the final be the same type of question, but different numbers or scenarios? So just to reiterate, this is the final pretty much that I gave after I'd finished where I'd finished last year. It has, you know, some meager correspondence to the final I'll be giving this year, but it's certainly not like I'm going to use the exact same questions. Like, I don't think I even put anything like number 3 on the real final. It doesn't have anything about cofunctions of complementary angles on it at all. So it's not like you just have to do the same thing for secant of 32 and cosecant of 58. This is good practice on all the stuff that we did so far this semester, and the final exam will cover all the stuff we did so far this semester. But I made no promises that this practice exam would bear any meaningful resemblance to the actual exam. It's just good practice. Tomas, did I answer your question? Hopefully. So anyway, I was saying 35 and 55 are complementary angles. The two acute angles of the same right triangle. So I'm going to continue by saying that the side opposite (55 degrees) would always be the side adjacent to 35 degrees. This is why cofunctions of complementary angles are always identical. How about I say identities? Cool. That's it for number 3. Let me just pause and say, Tomas, I certainly appreciate your question. It's a good thing that I had the chance to clarify that this practice exam is not exactly what's going to be on the real final exam. just what I gave last year. That is not an unreasonable question, though. And I do hope more people will ask more questions and not feel like they'll be attacked by me. Anyway, that's it for number 3. Hopefully no questions there on number 3. I will move on. Oh, again, same kind of deal. Like you should have mentioned those same things. You got to say something about the opposite 55 and the adjacent to 35. That would be like a critical piece. But your explanation wouldn't have to be exactly the same. Number 4. A derivation. Again, on the theme of what's coming up, like I'm pretty sure that the derivation of the law of sines is not on the real final. I can't remember. Maybe it is. Anyway, but you'll certainly have to derive something or other. Not the law, not Heron's law, but maybe the law of sines, maybe the law of cosines, maybe side ratios of the special right triangles, maybe some formulas for vectors. You'll have to derive something, but probably not the law of sines, since this was just on the practice final. So, the derivation for the law of sines, however. Let's draw some oblique triangle ABC. Arbitrary oblique triangle. I'm going to say here's angle A, angle B, angle C, side A, side B, side C. I'm going to sketch the altitude opposite or to side C. I'm going to say this is going to be called K. In that case, I can now say that over here in this right triangle, the red right triangle, it would be true that the sine of angle B is equal to the opposite side K over the hypotenuse A. And over here in this green triangle, the sine of angle A equals the opposite side K over the hypotenuse B. Solving both of these for K, I get K equals A sine B and K equals B sine A. That means that I can say by the transitive property that A sine B equals B sine A, and dividing by A times B, I can rearrange it such that A and A are together on the same side, and B are together on the same side, leaving me with, well, in this case, sine of B over B equals sine of A over A, which obviously from there it follows that sine of A over A would equal sine of B over B, just to get to exactly the ending I was looking for. QED. There it is. A proof. Questions on number 4. Cool. Number 5. Richard and Ryan, 2 of my students from last year, are on a boat sailing north along a coastline. Richard takes a sighting towards a distant lighthouse and finds the bearing to the lighthouse to be north 20 degrees west. After sailing 5 miles further north, Ryan takes another sighting, which shows that their new bearing to the same lighthouse is now north 25 degrees west. How far are they now from the lighthouse? So here they are. This is sighting 1. And let's see, northwest, so that's north and west. So the lighthouse is somewhere over here. Lighthouse. And at sighting 1, they're saying here is due north. I'm going to pause because I have a question. Jessica says, is there a size requirement for our page of notes? Like how big you have to write or how big the page is? Maritza says, can we write anything in the note card? You get one page. Maybe Jessica's asking like how big is a page? One page, 8.5 inches by 11 inches. Yeah, how big the page is. 8.5 inches by 11 inches. One page. You can use back and front. You can't photocopy anything. You can't use a printed page of notes. You can't photocopy someone else's handwritten notes. You can't print things out from the internet and shrink them down super small. You need to handwrite your one page front and back. But whatever you feel like writing on it, you can write on it. You certainly can't like stick other pages to it and then write on the back sides of those pages. You have to write on the one page that you got, front and back. Moose says, when do we subtract the bearing given from 90 degrees? I don't know, when you want the other side of the angle, is my answer to Moose. But not here, or at least not yet. But I think maybe we are going to do a little bit of subtraction in a second. So let's look at this problem. So let's see. I don't exactly love how close my, oh, well, I'm stuck there. Okay, but we're going to call that 25 degrees, even though it's clearly not 25 degrees. But here's their sighting. So they were sighting off at the lighthouse. Sighting off at the lighthouse. And this was north 25 degrees to the west. And then they go further north. Bearing to the saying 5 miles. Oh, no, the first one was north 20 degrees west. Sorry. North 20 degrees west. And then they go a little further north, 5 miles further north, and they take another sighting at this point, sighting 2. And, well, it's a curvy sighting. And now this angle is 25 degrees, north 25 degrees west. How far are they now from the lighthouse? And this distance here was 5 miles. So zooming in on this diagram, I know that if that was 25 degrees, then this angle here is what, 155 degrees, leaving me over here with an angle of 5 degrees. And I want to know what this side is, x. How far are they now from the lighthouse? So I'm going to say that the sine of 5 degrees over the opposite side, 5, is equal to the sine of 20 degrees over the opposite side, x. Which means that x over 5 equals sine 20 over sine 5. So x equals 5 sine 20 over sine 5. Pulling up my handy dandy calculator. Obviously, I'm just using Desmos because that's what I have on my iPad. You will not have Desmos. You will have scientific calculators, which work just fine. Or graphing calculators. 5 sine 20 over sine 5. Which we can see here is 19.62 miles. And yes, I'm still in degree mode. Good. X equals 19.6 miles. Questions about number 5. Let's see. I haven't really gotten at Moose's question, which is like here. There's a 25 and a 50 and a 155. So I've subtracted the bearing given from 180 degrees. I'm having another question. Leslie says, "Do I care how far you round?" I certainly care, Leslie, about all of your decisions, and I think that you make important and powerful and profound decisions, and I want you to be a careful and thoughtful rounder. But no, I'm not going to grade based on your rounding strategies. But anyway, let me see if I can't put this off to the side and address Moose's question, which was about the bearing and its complement. So let's say I had a bearing here and you knew that this was 58 degrees, and the question was like, what's the bearing? So again, this is not at all related to the question we were doing over here. This is just a different example because I'm trying to address Moose's question, which was, when do we subtract the bearing given from 90 degrees? I think this is maybe the situation he's talking about. If you saw that this was 58 degrees, the convention for bearings that is used in our textbook is that this would be north, and then I need to know how many degrees away from north, so that would be 22 degrees. Sorry, no, 32 degrees. My bad. North 32 degrees towards the east. So this given angle was 58, but when we go to write the bearing, it's north 32 degrees east, because the convention that our textbook uses is we always start with north or south and then write the bearing as a rotation away from north or south towards east or west. Now, another way that like our snapshot writes these same bearings is like 58 degrees north of due east. That's another perfectly reasonable way to talk about that bearing. Also, we had another group of problems in our snapshot where all of the bearings are away from due north. So that would mean that this is 90, 180, 270, let's see, 328 degrees away from due north. Those are all perfectly reasonable iterations of this bearing. Moose, did I answer your question? Hopefully. Again, just to reiterate, this whole picture and these bearings have nothing to do with problem 5. Problem 5 was previously answered. The answer was 19.62 miles. Cool. Moving on to number 6, which says that to approximate the area of a lake, Samantha walks around the perimeter of the lake and takes the measurements indicated on the diagram below. Find the total area of the Pentagon. Now, earlier Tomas had asked, are you going to give just the similar questions with different numbers. I'm pretty sure there is a question that's pretty similar to this one. On the real exam. But going back. So I tried to say this multiple times, Maritza. This here was the answer to number 5. This is number 5. I had bearings of 20 and 25 and 5 and sine of 5 and sine of 20, and that got me 19.62. This over here was a question that came up in the course of my work about bearings. And it was an example that I was trying to explain to respond to a question. Completely not related to number 5. Cool. Okay. Number 6. To approximate the area of a lake, Samantha walks around the perimeter of the lake and takes the measurements indicated on the diagram below. Find the total area of the Pentagon. So they have nicely divided the shape up into 3 different zones. I'm going to shade it as a green zone, a red zone, and a blue zone. I'm going to say that for the green zone, I could use the area of the green zone could be given by area equals 1/2 BC sine angle A, such that area would be 1/2 100 times 125 times the sine of 50. And I'm going to plug it in here that area 1 equals 100. Oh, sorry. 1/2 times 100 times 125 times the sine of 50. Cool. And then area 1. The red zone I'm going to come back to. The blue zone I'm going to call area 3 is also 1/2 times 50 times 70 times sine of 100. 3 equals 1/2 times 50 times 70 times sine of 100. And 1723. Okay. Now, let's see. I want to get the area of the red zone. So area of the red zone, I need some more information. So I don't have, I really only at this point have this one side. I certainly can't use 1/2 BC sine C. I'm going to need to find this side and this side. And as soon as I have 3 sides, I don't need to worry about any angles because then I can use Heron's law. So in order to find this side and this side, I'm going to need to use law of cosines on both of these 2 sides. So I'm going to use law of cosines here on this triangle to get this side, and law of cosines over here on this blue triangle to get this side. So let's see. I'm going to call this side side x, and this side y. And I'm going to say that x squared would equal 100 squared plus 125 squared minus 2 times 100 times 125 times the cosine of 50 degrees. And by the way, I'm just using c squared equals a squared plus b squared minus 2ab cosine c. Okay, so I'm saying x, and I'm going to name this x1, is equal to big square root 100 squared plus 125 squared minus 2 times 100 times 125 times the cosine of 50 degrees. I lost sight of that, so I need a little more space here. There we go. So x looks like 97.75 feet. That looks pretty nice. X equals 97.75 feet. And then I'm going to do the same thing for y, saying that y squared equals 50 squared plus 70 squared minus 2 times 50 times 70 times the cosine of 100 degrees. And in Desmos, it's nice to name it not y, because then it'll start graphing, and I don't really want it to graph. So I'm naming it y1 square root 50 squared plus 70 squared minus 2 times 50 times 70 cosine of 100. And it looks like value of y is 92.82. Cool. And the nice thing about working in Desmos and having named all these variables is that I can now just say that the red area, area 2, will be given by Heron's law. And, oh, that made it too big. Heron's law says that the red area, area 2, is equal to, let's write out s, the square root of s times s minus a times s minus b times s minus c. That's Heron's law. So in this case, it's going to be the square root of the semiperimeter. Semiperimeter S equals 50 plus x1, which was 97.75, plus y1, which was 92.82, all over 2, 120.28. So I've got 120.29 times 120.29 minus side A, which is 50, times 120.29 minus side B, which is 92.82 times 120.29 minus 97.75. No, that didn't work. 97.75. Whew. Cool. So I'm going to say here, tell Desmos that area 2 is equal to the square root of s times S minus 50 times S minus x1 times S minus y1. 2,287.48. Area 2 equals 2,287.48. Going back here, just because I realized I didn't put in the other areas. If you didn't see it, area 1, the green part was 4787.78, and the blue part was area 3 equal to 1723.41. And now the grand total, area 1 plus area 2 plus area 3. Two plus area 3, 8798.67. Total area 8,798.67 square feet. Okay, there's question 6. Questions on question 6. Looks like we're pretty good. Moving on to number 7. Compare and contrast the law of cosines, the law of sines, and Heron's law. Be sure to discuss their derivation and applications. Okie dokie. Gonna grab a keyboard for this. Let's see. Start with derivations. The law of sines, cosines, and Heron's law are all derived by dropping an altitude in an oblique triangle to create two right triangles, and then applying, that's not it, applying the tools of right triangles to create a system of equations which we solve to generate the 3 laws. That's a good comparison. The law of sines uses right triangle trigonometry, sine ratios. The law of cosines uses, let's see, the Pythagorean theorem and right triangle trigonometry, sine, and Heron's law uses just the Pythagorean theorem. And that's it. Okay, so that was their derivations. This is pretty small on your guys' screen, huh? Should I make it a little bigger? I don't know if that's all that much better. Underline. Okay. Applications. All three formulas should be applied to solve for features of oblique triangles, though they would all also be true in true is not right. How about all also yield correct results in right triangles? There would always be a simpler method in a right triangle. The law of sines can be used to solve for side lengths given angle, side, angle, or angle, angle, side, and for a missing side given side, side, angle. Noting that side, side, angle may be an ambiguous case. The law of cosines can be used to solve for side lengths given side, angle, side, or an angle given side, side, side. The law, Heron's law can be used to find area given side, side, side. Cool. Important things I missed? I think I talked about derivations and applications. There's some comparisons and some contrasts. That's pretty much what I got. Let's see. So the red is compare. The blue is contrast. Certainly there could be more detail. This isn't the end-all and be-all comparison. Ooh, that's a great question. I don't know. I'm guessing that's Katie Aquino. And she says, can we reference the trig map? The trig map is totally a good thing to have ready on the final exam. It well might be useful. But if, Katie, you mean by referencing it, you mean you should talk about what it means, right? Not just say because of the trig map. Maritza asks, how many problems does the final have? Has 9 problems. Ooh, Moose, that's a great question. Ambiguous case, is that coming up on the final exam? Yeah, probably. I would say yes, it's coming. So Maritza, I'm agreeing with Maritza saying yes, totally reference the trig map. Like know the trig map, that's a useful tool, and be able to discuss what it means and why it means what it means. So let's see, I was saying these are comparisons. That was poorly done. A little more space. Moose appears to be sad that ambiguous case is coming. And in blue here we have contrasts. Maritza, on the other hand, is very excited about the ambiguous case. That's good to hear. Katie's also excited about the ambiguous case. Wonderful. Some students with good attitude. Hurrah. That's clearly worth a few extra points. It's just good attitude. Other questions about number 7? Obviously, like I said, like with all these explanation ones, this is not the end all or be all. This is kind of what I said off the top of my head. Kind of covers the things that were asked in the question. There's certainly some things that you would certainly have to get at, but there could be more that you could have said. Other things that you could have said. Wording could have been totally different. Again, referencing Tomas's question a while back, the actual exam is going to look different than this one. It's not like you get the same exact problems with just different numbers or anything like that. But you might well see a similar thing of being able to know when to use the law of cosines, when to use the law of sines, when to use Heron's law, when to use right triangle trig, that kind of a deal. And Vu asks, can you review an ambiguous case and what we would be looking for in that case? I can do a problem involving the ambiguous case, certainly. But I'm going to start. Vu, should I do that first, or should I go over the vector stuff? We got about half an hour left. Vector sounds good. Ooh, but Maritza says an ambiguous case. Well, I'm going to do this one vector problem because I think this one was kind of a doozy. And then I'll go over ambiguous case. So we had the angle alpha between the positive x-axis and the vector u is 135 degrees. So let's see. That's kind of a crooked y-axis and sort of a crooked x-axis. And vector u 135 degrees. So it's going to be over here. 135 degrees, and the magnitude of u is 10. And then for another vector v, there's 210 degrees all the way around, so 180, 30 more. Magnitude of v is 12. So okay, I'm back. We had some brief problems, but they were at headphones, and we're back on my screen. Okay. Hopefully Maritza is not actually dead. I doubt that she is, because then she wouldn't have been able to type "am dead." Jennifer does seem unhappy and has said, ah, ah, ah. Jennifer Lee is worried that no one else got frozen. Maritza got scared because she saw my face. My face is scary. Agreed. This is the most participation we've had. All night long. As soon as I go away, then everyone starts talking. You don't talk when I'm, trying to get you to ask questions, but as soon as there's other things, all kinds of conversations. Okay, so there was, in the course of all of that discussion, one actual question. What is the trig map? Tracy had a math question. What is the trig map? The trig map, yes, Tracy, you. The trig map was like a diagram where we talked about like kind of when to use what tools where. So we said that in right triangles, there would be sine, cosine, tangent, inverse sine, inverse cosine, inverse tangent, the Pythagorean theorem. That if it's an oblique triangle, we're going to use different tools depending on whether it's side, 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 angle, side, angle, side. Oh, now she figured out what I'm talking about. Okay, cool. Yeah, the organizer, kind of a graphic organizer. Elizabeth says someone call Dr. Phil. Oh, forgot about the self-confidence, right? Self-confidence for sure. Yeah, Moose is on it. Side angle side, law of cosines. Katie says it's a bunch of arrows. Yeah, that's the trig map, a bunch of arrows. Thank you. That's the one. I think Tracy's figured it out, the thing we're talking about. Amy, even if I was unable to reconnect, there still would have been a final. Certainly, I make no promises that the
live chat works or continues to work or is useful to you, you'll still have a final. I think it's helpful. I also think it's kind of fun. But it does not mean that there would or would not be a final just because this works or does not work. Anyway, should we talk about number 8? Jennifer suggests a prayer circle. Maritza is worried about confidence. Shaheen says, yes, we should do number 8. I don't know what KMS means, but let's go ahead and do number 8. So, number 8 says, I think I've set it up reasonably well, 210 degrees, 135 degrees. Maritza, I'm thinking we probably should not talk about that right now. If you want to have a conversation about that, maybe another time would be more useful. I actually have a ton of fun with our class. I don't think it's suicide. Anyway, number 8. Find the direction angle alpha and the magnitude of the vector u plus v. Is our first step A. So let's see. In order to find the sum u plus v, I want to visualize that. I'm going to visualize it by saying I could take the blue vector and bring it to the end of the red vector. Obviously, I could also take the red vector and bring it to the end of the blue vector. Either way is going to be a reasonable method of finding the resultant or sum of the two vectors. So I'm going to say here's a copy of the blue vector. And I'm going to place it at the end of the red vector. Cool. And this is a good example because it's kind of unclear whether this would be above the x-axis or below it. So we're going to actually have to think about the trig to think about the direction angle because I'm not really sure if it's above or below at the moment. But obviously it's somewhere over here. And here's the resultant vector. Okay. So I know that the angle between 135 and 210, 210 minus 135 is what? 65, 75 degrees? So this angle here is 75 degrees. And that means that this angle would also have been 75 degrees. And that means that this angle must be 105 degrees. And then I can use that angle between the two vectors to use the law of cosines to get the length. So c squared equals 10 squared plus 12 squared minus 2 times 10 times 12 times cosine of 105 degrees. So let's see. I think I'm just going to use a calculator. Put it over here. We'll go over here. Yeah, it goes over here. Cool. So this is all from earlier problems. Get rid of all that mess. And let's say that side C is equal to the square root of 10 squared plus 12 squared minus 2 times 10 times, oh, that was not a 10, 10 times 12 times the cosine of 105. 17.49. Okay. So magnitude of u plus v is 17.49. And then I would also like to know what's the direction angle, alpha. So how many degrees are there here? So I know I went 135 degrees to get to this red vector. If I could find the angle here, I could add it to 135 degrees, and that would tell me how many degrees I go all the way around. This is alpha. So I'm going to say to find the yellow angle, I'm going to call the yellow angle theta. To find theta, I want sine of 105 over 17.49 equals sine theta over 12. So let's see. Sine theta equals 12 sine 105 over 17.49, which makes theta the inverse sine of 12 sine 105 over 17.49. I'm going to need a calculator for that. So inverse sine of 12 times sine 105 over 17.49. Oh, let's just use C because I have it precise. 41.49. So theta equals 41.49. Now I'm going to add the 135 and theta, 41.49, and that makes 176.49. So plus 135, 176.49. So you can see I drew it correctly. I drew the green hopefully a little bit above the x-axis because it's not going a full 180 degrees. It's going a little bit above that, 176 degrees. So alpha equals 176.49 degrees. That's the angle alpha between the x-axis and the resultant vector u plus v. Now I'd like to write that new vector, write a new vector u minus v in component form. Okay, so working in component form is another way to approach these problems, which is why I gave you kind of the two parts. Is one, we can find the angle alpha and magnitude using the law of cosines. Also, we can subtract and add vectors by writing them in component form and then adding or subtracting the components. So I'm going to go ahead and ditch all this. Let's see. I do want that answer back. It was magnitude of u plus v equals 17. What was it? 17 point. 4, 9? Cool. Okay. And now I want u minus v. So now u minus v is going to look more like this green vector. So go forward. So here's u, and then go backwards v. So forward u, backwards v. And pull them apart. So minus v goes exactly the opposite way. So u, forward u, minus v. So forward u minus v would look like that. And there's the vector that goes forward u and backwards v. Now, just kind of a quick thing to notice is that u minus v, here it is with u in its original position, and I've made it so negative v is at the end here. Just for reference sake, that's the negative v vector. But we could have done u minus v just by saying u minus v is the vector that goes from the very end of v to the big end of u. That's also u minus v. Those would go here or there. Those are both ways to visualize u minus v. No, this is a little bit off there. So it should be kind of more like that. And then it'll fit. Does that fit a little better? That fits a little better. U minus v. Either way. And we want to get u minus v in component form. And like I was mentioning, another way to approach these problems is by working in component form from the very beginning. So u in its component form, let's see, 135 degrees and a magnitude of 10. So I'm going to go in and say u has two components, an I component and a j component. It's a nice 45, 45, 90 triangle. So that means that this is 5 root 2 j going up. And this is negative 5 root 2 I going left. So u could be expressed as negative 5 root 2 I plus 5 root 2 j. And then vector v is a 30, 60, 90 triangle. So thinking about its horizontal component and vertical component, we can say 12, well, that's 6, and this is 6 root 3. So negative 6 root 3 I minus 6 j. Okay, and then I want to subtract them. I want to do u minus v. So u minus v equals negative 5 root 2 I minus a negative, so plus 6 root 3 I plus 5 root 2 j minus a negative, so plus 6j, which is looking like the time to approximate. So approximating, I've got negative 5 root 2 plus 6 root 3. So negative 40.3. Oh, whoops. Negative 5 root 2 plus 6 root 3. That's better. Negative or positive 3.32. That makes more sense. 3.32i. And then the j components, 5 root 2 plus 6. 13.07. There's my answer. The vector u minus v in component form. Now, find the angle between u and u minus v. So the angle theta between u and u minus v would be given by u dot v over the magnitude of u times the magnitude of v, and that will tell us cosine theta. So in this case, I'm going to say cosine theta equals u dot u minus v, knowing that u minus v is really kind of one vector, over the magnitude of u times the magnitude of v. Okay, so for vector u, I had a1, b1, and for vector u minus v, I have a2, b2. And when I do u dot u minus v, I'm going to say a1 times a2 plus b1 times b2, which is negative 5 root 2 times 3.32, which I'm actually going to name that a2. And then plus 5 root 2 times 13.07. So let's figure out what that is. 13.07, that's B2. Okay, so A1, negative 5 root 2 times A2 plus 5 root 2, that's B1, times 13.07, that's B2. 68.94. And so now I'm at cosine theta equals 68.94. And I need to figure out what's the magnitude of u times the magnitude of v. So the magnitude of u, I know, Oh, shoot. This should have been u minus v, huh? Sorry about that. Magnitude of u is just 10. And the magnitude of u minus v, I need to figure out. But it's square root of a squared plus b squared. So it equals square root of a1 squared. Oh, a2 squared plus b2 squared. 13.48. And 10 times 13.48. Okay, so theta equals the inverse cosine of 68.94 over 10 times 13.48. $59.24. Whew. Well, that one was fun. Questions there? The lag has gotten pretty bad. It's going to be like 10 seconds before everyone can see what I'm actually doing. Tracy and McKenna somehow think that this wasn't fun, which is ridiculous. They clearly have impoverished definitions of the word fun. Moose says the u minus v vector tripped me out. How did I form those 30, 60 triangles? Maritza also doesn't know what fun is. Jennifer does. But Moose actually had a real question. So we were looking at so 135 here, Moose, it means that there's 45 here, right? 45 degrees. So that means this is 45 degrees, and obviously that's 90. So I was looking here at this 45, 45, 90 triangle, and I said 10 x root 2 over 2, x root 2 over 2. And then 210 degrees takes me 30 degrees past 180. So this is a 30, 60, 90 triangle. 90, 60, 30. And so that means if this is 12, then this base is half the hypotenuse, and this is 6 root 3, base times root 3. Hopefully that helps, Moose. Yeah, I mean, really, I formed my own line for both the I and the J, right? There was no line in here that was just that long, but I drew it along the x-axis to go over I, and then parallel to the y-axis to go up J. And then same thing along the x-axis to go backwards I, and then parallel to the y-axis to go down J. So really, both the I and the J components I kind of drew in there. Just because it's not super clear, let me mention this here. That's the answer to part B. And this was all work we did for part C. And there's the answer for part C. And this, I think, is pretty clear as the answer to part A. Any other questions about number 8? Or should we move on to number 9? Cool. Number 9. Uh, Alexandra and Lorena have hung a 1 kilogram mass from a climbing anchor they set up. The spring scale on the left shows a force of 6 newtons. The scale on the right shows a force of 9 newtons. Lorena measures theta 1 is 28.28 degrees. Then 1 is the measure of 2. Melissa, Shaheen says, what about the ambiguous case? It's now 8:30, which is when I said I was going to stop. Maritza says, yes, I never talked about the ambiguous case. I believe, Maritza, that I did spend a couple days talking about the ambiguous case this semester. It's not something that we just made up tonight. Melissa's wondering if this entire process would be on the final. The answer to that question is, I mean, you certainly need to know about Maritza's. Or sorry, you need to know about vectors. Maritza needs to focus on the big picture. Um, the final doesn't have the same question, Melissa. It's got different questions about vectors, so different processes. Some of the questions might be difficult and have a long process. Other questions might not. Um, I think I could talk a little bit about the ambiguous case, but that wouldn't really leave me much time to talk about 9 or 10. Maritza, that kind of attitude makes me really have no interest in moving on. I understand you're stressed. I think I can do a little more time. I think that's what we will do. But that attitude makes me think that I should not do this in the future because students are going to whine or feel like this review session is the only thing between studying and the end. I think it's nice to help out before tests and quizzes. I know you guys are stressed, and I want to be helpful. But if I can't get to something, then I can't get to something. And the big idea is that you learn how to do the math all semester long, not right before the test. So, number 9. Oh, Jessica has a good question. What chapters in the book were we on? Let's see. Let me go here and then here. Chapters we've covered. 8.1, 8.2, 8.3, 8.4, 9.4, and a little of 9.5. I'm going to generate a force diagram. I know that theta 2 has the greater force of 9 newtons. And I know that the weaker force is going to be over here, only 6 newtons. And I know that the force pulling down would be 1 kilogram, so 10 newtons. And we're trying to find this angle, theta 1, theta 2, and this angle, theta 1. And Moose is pointing out that fourth period students are looking at a problem that has all of this, but not 28.28. Exactly. Fourth period probably got a different sheet. I noticed that if I didn't make it 28.28 degrees as theta 1, if theta 1 was not given, then it's a pretty hard problem. And I was trying not to make you stress, so I edited it a little bit for sixth period for the level of problem that we would see on the actual test. So, like Moose is saying in the chat, fourth period has a different sheet. You should add in that I'm giving you theta 1, 28.28. And all you have to find is theta 2. Solving for both angles is a much more difficult problem. Okay, so we've got 28.28 degrees given. And we're going to solve for theta 2. And we know a couple things. We know here that the right side and left side forces ought to be balanced. So here's 6 cosine 28.28. And on the other side, the right side force, 9 cosine theta 2. So these two forces need to be balanced. Left force equals right pulling force, which means that 6 cosine 28.28 equals 9 cosine theta 2, giving me cosine theta 2 equals 6 cosine 28.28 over 9. So theta 2 equals the inverse cosine of 6 cosine 28.28 over 9. Pulling up a calculator. 54.05 degrees. I got 08. Tracy says the reason she got 08 and I got 05 is that it's her calculator. But yeah, basically right. Cool. Questions on number 9. Yeah, and then I'm leaving a note. 4th period. Add in that theta 1 is given 28.28 degrees. It was solvable. I solved for the original 4th period problem and got 28.28 degrees, but the problem is just a lot harder. So too hard otherwise. Moose, we're done. We found theta 2. That's all the problem is asking now. We didn't have to use a system of equations at all. The way I had originally given the problem, we had to find both angles. It was a system of equations, but solving the system of equations was pretty difficult. You either had to use trig identities or a graphing calculator. So I just made the problem easier. Cool. Moving on to number 10. Let's see. We've got me skiing up Castle Peak at an incline of 34 degrees. There are my skis. There's me. My force due to gravity pulling straight down is 210 pounds. But we want to decompose that into a portion of the force that's directly normal to the slope of the hill, and the portion of the force that is going to have to be held up by friction, which were provided by the skins of my skis. So we want a portion X and a portion Y, and we know that if this was 34 degrees, then because this is a right triangle, there'd be 56 degrees right there and 34 degrees right there. So saying that the sine of 34 degrees is equal to the opposite side over the hypotenuse 210. So the force of friction would need to be 210 sine 34. Or 117 pounds of friction. For 3 pounds of friction. N questions on number 10? Yeah, I'm going up the hill. Up. For show. Straight up. If there are no questions on number 10, shall we look at the ambiguous case of the law of sines? Am I using sine because, no, I'm using sine because I was interested in this portion of the force, and sine, Michelle, relates the opposite side to 34 to the hypotenuse. Sine is opposite over hypotenuse. So I'm using sine because this is the part I want. It's opposite the 34. And because I know the hypotenuse, 210 pounds. Jason, you seem to have a very poor idea of what the idea is behind this. Why on earth would I give you extra credit for watching this? The idea is that you learn stuff. If you didn't need to learn it, you shouldn't have watched it. Go to sleep. Shaheen says, how soon will the problems be posted on Classroom? I don't understand what you're saying, Shaheen. When will this video post on Classroom? As soon as we're done. I'm glad to hear you were joking, Jason. Those kinds of comments and some of the comments that came earlier make me a little worried about these review sessions. Perhaps they sometimes have a different impact than what I intend. When people start feeling like if I don't cover something, then they're going to fail, that's not the idea. When people start looking for extra credit just for watching, that's not the idea. The idea is to go over some of the things before the test. That's it. Okay. So the law of sines, we have our trig map, which has come up earlier and is a great thing to be real clear about. When to use law of sines. So sometimes we use it because we have angle, side, angle. Sometimes we use it because we have angle, angle, side. And in both those cases, we're going to find a side. And sometimes we use it where we have side, side, angle. And this one is potentially ambiguous. And the reason it's ambiguous is because you have a given side and a given angle. So you have this side 1 and this side 2 and this angle theta. Then side 2 has 2 potential spots it could go. This is one spot side 2 could go and it would form a triangle. But also there could be the same side too. And it might be right here. So both of those are potential triangles. Side 2. Are we talking about this triangle, or are we talking about this triangle? They both have the same side 1, the same side 2, and the same angle theta. Side, 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 or side, side, side. We don't know which one is being addressed just from the side, side, side. Now, this doesn't always happen, but it might happen given side, side angle and trying to solve using the law of sines, which is why we call it the ambiguous case. So, there's different things to look out for. I'm going to just go on the internet and look up an ambiguous case of the law of sines problem, just so I know I find one that works. So here we go. 33 degrees, 6 inches, 10 inches is the first one I found on the internet. So I'm saying, what happens if we know that an angle C is equal to 33 degrees, maybe a side C equal to 6 inches, and a side B equal to 10 inches. So, for example, so this is pretty similar to what I just drew. The 33 degrees, 10 inches. And the question is, does the 6 go there or does the 6 go there? And we're going to solve both triangles. There might be relevant information in either triangle. Let's solve both of them. So either way, I'm going to start by saying that the sine of 33 over 6 is equal to the sine of, let's see, angle B over 10. So sine angle B equals 10 sine 33 over 6. And angle B is going to equal the inverse sine of 10 sine 33 over 6. $65.19. Okay, so the angle I just solved for would be if the triangle was arranged like that. 65.19 degrees. Now, because this 6 here It's 6 going that way and 6 going that way. That makes this a little isosceles triangle in blue, which means that this would also be 65.19, which means that this triangle and this other triangle, the angle in the other triangle, is the supplement of 65.19. So I'm going to say, what's 180 minus 65.19? And it's 114.81. Okay, so now I've got two angle B's. Angle B number 1, 65.19. Angle B number 2, 114.81. Okay, now what else am I going to solve for? I'm going to solve for, how about angle A? Angle A number 1, well, I've got 65 degrees, I've got 33 degrees. So I'm going to put all this in here. Angle B number 1, angle B number 2, I've got 33 plus angle B number 1, be 98. So angle A in triangle number 1 is 81.806. 81.806. So that's this angle A. 81.8 degrees. But angle A could also be this. So let's say, what's 180 minus 33 plus B2? 32.19 degrees. 30.19 degrees. And then last thing I need to solve for is side A. So side A, so I know that sine 33 over 6 will equal sine of 81.81 over side C. So C equals times sine 81.81 over sine 33. $10.904, and this is C number 1. Okay, so this is in triangle number 1. This entire distance would be 10.904. And then C2. If we were thinking about the other triangle, the smaller triangle, we would have the same setup. Sine 33 over 6 equals sine of the other angle A, 32.19 over C2. So that C2 would equal 6 sine 32.19 over sine 33. 5.87. So back in my image, 5.87. C equals C2 equals 5.87. So that was an example of what the ambiguous case of the law of signs means and what we would do if we were faced with a problem where we had to solve a triangle involving the ambiguous case of the law of signs. Tracy's mentioning that sometimes it's not clear that there are two solutions, and you have to figure out whether it's possible for the triangle to have two solutions. So the way we would do that, Tracy, is we would say, okay, for this angle theta, once we get 81 and 32, we would check. If 81, in this case, 81 and 33, oh no, sorry, 65 and 33, it was possible to have a triangle involving 32. And then again, 14 and 33 both have a triangle, and we would have this angle A, angle B, and angle C, or we could have this angle A, angle B, and angle C. Both of those were possibilities. If we hadn't gotten 65, and let's say instead we had gotten maybe 40 degrees. No, that would still work. Let's say we gotten 30 degrees for angle B1. 30 degrees means that the supplement here would have been 160. But if we do the supplement would have been 150. If we do 150 and 33, that makes 183. That's not possible. There would have been only one solution. But I'm not really going to tell you exactly what's on the final or not, Tracy. You should know how to solve triangles involving the ambiguous case. You should know how to decide if there's no solutions, one solution, or two solutions. Those are things we covered. If you want to look for more practice on that topic, it's in section 8.2 on the law of signs, and I think the questions there are questions 25 through 35 are all practice on the ambiguous case. Section 8.2, 25 to 35. Any other questions? Okay. Not seeing any. Apologize. Frustrated with some of the attitudes. I think that this is a neat thing to do. I like being able to do it. I do think that it sometimes has a tendency to encourage some bad habits and some bad ways of relating to math, to just watch someone else do it and then try to memorize it. And so I'm always cautious when I do these, and I am wary of those bad tendencies. And so when I get frustrated, it's not necessarily that I'm frustrated with you. It's more that I'm frustrated with me and that I've set up a situation where we're learning to follow bad habits. Rather than focusing on the big learning that happens over the course of the semester, we instead get focused on trying to figure out what's on the final, or learning to do it right the night before, or getting extra points, or not having a final because something didn't cover it or the movie didn't work. And none of those things are the ways we should be relating to mathematics, or to school, or to thinking, or to thought, or to truth. or to ideas, or to technology. These are all terrible ways to relate. And I want to encourage you to relate in better and more healthy ways. So that is a source of my potential frustration. Anyway, seeing still no further questions, I will just say that good luck with your studying. Hopefully you're feeling well prepared and you'll just go to sleep and get some sleep before the exam tomorrow. And I will see you all either tomorrow for 4th period or Thursday for 6th period. Hopefully this was useful. I'll talk to you all later.